Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. If you visited Florida's Gulf Coast and headed to the beach, there's a chance you might have encountered a respiratory irritation issue, occasionally even a severe one. A likely cause of such irritation is known as red tide. Fortunately, a dataset going back to 2011 exists, which is helpful in monitoring this phenomenon. Today on the show, I speak with Shane Ross about his work developing 24-hour forecasts of red tide-induced respiratory irritation and the time series methodologies used to do it.
I'm Shane Ross, and I'm a professor of Aerospace and Ocean Engineering at Virginia Tech.
Welcome to the show.
It's good to be here.
Broadly speaking, can you tell me a little bit about what your areas of interest are? What do you study?
Well, I have a lab that studies a variety of aspects of dynamics, and this is dynamics broadly defined. So anything that changes over time. Some of our bias has been looking at environmental systems and things moving through the air and the water, particularly biological agents. But also I do some first principles modeling of engineering applications related to aerospace.
So I know a lot of my audience comes from a machine learning perspective or a data science point of view, and perhaps bring this bias to the table where you think, just give us the data and then we'll go find a model. And that can work fine in some contexts, but I know in a lot of the things you study, it's sort of the other way around, right? Can you describe the process of modeling from your perspective?
Often the problems that I've looked at have related to things transporting through an environmental fluid. So the atmosphere or some aquatic medium like the ocean or a lake. So we take the point of view of typical fluid-based transport. So how does material move? And if there's anything on top of that, like some biological or chemical process happening, that just gets added on top of the fluid mechanics.
Well, the paper I invited you on to do a deep dive about is titled Beach Level 24-Hour Forecasts of Florida Red Tide-Induced Respiratory Irritation. So a couple of things to unpack. Maybe we could start with, what exactly is the red tide?
So red tide it's a name given to this phenomenon that seems to happen a lot in Florida, but also throughout the Gulf Coast and many coasts throughout the world. It's an algal bloom, and it's called a harmful algal bloom because of how it affects people, but it just means that algae have grown to a level that sometimes it's actually visible as red water. But the Florida red tide, it's not something new. It was first seen recorded by Native Americans hundreds of years ago. It's something that comes periodically, and when it's at high enough levels, it can cause respiratory irritation effects. It also leads to death of fish. It has a big economic impact along the coast.
So a simple heuristic I could follow would be don't swim in red waters. That'll probably save me from the worst of conditions, but I presume there are also circumstances when beachgoers might unknowingly put themselves at risk. Is that correct?
Well, I guess you're talking about swimming in the water, right? That aspect of it I'm not as familiar with. I don't think it leads to that much irritation for people swimming in it, and it's often not at those high enough levels. You will feel it and experience it from the respiratory point of view long before you get in the water if it's bad enough. It's a lot like a chemical agent that they might use in warfare. It affects you immediately. So when I went down there with some of our researchers, and we felt it immediately when we got within maybe 300 feet of the shore. It just starts making you cough and sneeze, and it's pretty unpleasant. And we weren't there even on a very bad day. It was more of a mild day.
Gotcha. So if we knew when those days were, maybe, I guess, we could take actions, shut down the beaches, that sort of thing. How predictable are these bad conditions?
The red tide shows up as a bloom. A bloom is defined as, say, a long-lasting and over a large geographic area of red tide. And knowing when those things show up, that's a very long time scale type forecasting problem. That we're not able to forecast so well. But once a red tide bloom does show up, it has very patchy effects about where and when it's present in extreme enough levels. And that we think we can forecast probably one day ahead of time.
What's the limit there? Like, I'm told a lot of the accuracy that's increased in predicting the regular old weather of the planet Earth has in part come because computers have just gotten faster and faster. That there was a point where making the 4-hour forecast took 8 hours, so what good was it? Are you hitting those limits, or is it the limits of your data, or maybe all of the above?
Well, I mean, unlike the weather, I think we don't have as good an idea of the spatial distribution of this algae in the water. So that's affecting things. I guess you're asking, like, are we coming up against some hard limit, like 10 days forecast? I think we're nowhere near that. I think we're just starting to attack this problem because it's now affecting large population centers. There's millions of people who live on the Gulf Coast of Florida, and these red tide events have been increasing in frequency and intensity. So there's just been more interest in attacking the problem.
And that 24-hour forecast you're working on, is that an ideal time period, or is that just the conditions are right to make that prediction? Why not 12 or 48 hours or something like that?
It's based on the data that we're using. So we're taking from a 10-year database where the data was collected about once a day. So that just gave us the time horizon. So we're basically just training on this data set that kind of had a 24-hour timescale built into it.
Yeah, let's talk a little bit more about that data set. That sounds like a great resource, 10 years of observations. How did that come to be, and what's the nature of the data set?
Well, it was started by the Moat Marine Laboratory and Aquarium in Sarasota, Florida. It's called the Beach Conditions Reporting System, and it started in about 2006 with a few beaches reporting, and now it's got up to 40 beaches. It's a data set where mostly lifeguards and park rangers are the primary reporters in several counties, and also some data, also some citizen scientists will report into this. And twice a day, they'll report things such as the presence of dead fish, the color of the water, the quality of the waves, the height of the waves, and most importantly for us, the level of respiratory irritation.
And how do you measure the level of respiratory irritation?
There's a 4-tiered irritation level that goes all the way from none to high. And basically, it's the amount of coughing and sneezing heard within 30 seconds. But when it's very high, then nobody's showing up at the beach. So lifeguards just sort of have an idea of what it feels like. So in some sense, it could be a subjective data set, especially on the days when it's very high and people just sort of know to stay away from the beach.
I mean, I guess in some ways the lifeguards' attentiveness could weigh into it with a small variance. Do you see anything like that? Or, just given a 4-point scale and the fact that you have trained people, on a job trying to accomplish this, do you get a relatively homogeneous set of observations?
We seem to, and part of it is that the lifeguards set to a baseline because they move around, so they're not at the same beach. So we'll have lifeguards from different beaches, and they usually will report together. There's usually 2 to a station. So they'll sort of agree that, yeah, this feels like a moderate day, or this feels high. So there's rough agreement across the reporters.
So then it seems like you have a nice time series problem where, depending on how you want to slice it, you've got many years of data to look at, and you're trying to essentially predict tomorrow's irritation score. Is that correct?
That's right.
And then let's talk a little bit about the modeling approaches. I know you've taken 2 in the paper. Maybe we can start with the first, which to my ears seems to be a simpler one. What's the initial way to try and model out and make a prediction like that?
The first model we looked at that seemed more intuitive, at least to me, is a wind-based model. So it's known that the respiratory irritation, it comes from when the bacteria, the algae, break apart due to wave action. They release a chemical that just happens to cause irritation to us, and this happens offshore. So if there are onshore winds coming from the ocean to the land, then that tends to lead to days of higher intensity. Whereas when it's offshore winds, going from the land back to the ocean, you should have less intensity or no intensity at all. So we use that as a first model based on 10 years of data where we know the wind conditions and also the respiratory level.
So then it's almost like forgive me if this is an overgeneralization, but the red algae is emitting this exhaust and the wind is either taking it to shore or away. Is that the sort of a fundamental of it?
Yeah, that's the basics of it. If it's present in the ocean, But just sort of staying in the ocean because the winds are blowing it back, then yeah, you won't feel anything on land. But yeah, that's a great way to characterize it.
And so you've gotten that because you have this rich data set available. Would there be other things you might be interested in having, like maybe some prediction about whether the algae, were positioned in the ocean? I know it seems like you're kind of picking it up at the 11th hour almost. Or is that just the nature of the data you have, or is it so dynamic you can't make a prediction till it's really about the irritants coming off the water?
It can change pretty rapidly. So it's been reported that it could be very high respiratory irritation 1 hour, and then 2 hours later, it drops down to low or none. And we also do not have a good spatial resolution of where this is in the water. There are groups that are doing sampling of the water to find the presence of the algae, but that takes a couple of days to even get a concentration number. And by then, things could have moved due to ocean currents, due to wind, due to wave action. I mean, if we really threw all of our efforts at this, there's a lot more data that we'd want to take. For now, in some sense, we're using the human lung as a sensor because it's really good at detecting the level of, even at the level of nanograms per liter of this toxin that's in the air.
So given the model you described that primarily looks at wind movement, how accurate can you get in the predictions?
So using the wind-based model, the highest accuracy we're able to get is 85% accuracy. So knowing today's level of respiratory irritation and the wind tomorrow, we can forecast what the level will be tomorrow, 85%. That's the highest. The lowest is 79%. We looked at 8 beaches. So on average, it's about 82%.
And then from a practical point of view, does that make it useful enough that someone can take some action based on that? Whether it's the closing of the beaches or some warning signs, is 85% or whatever getting actionable in a way?
I would think anything over 50% is actionable. And we've talked to people in the public and even interviewed people along the beach who said that, oh yeah, red tide's a big deal. And if some forecast was available, this could help them plan their day, plan whether they want to go play beach volleyball or maybe they just want to stay away from cafes near the beach that day.
Let's go on to the other modeling techniques you explored. What else was an interesting way to approach the project?
We used a self-exciting Hawkes process model, which is it's an inhomogeneous Poisson process model. We don't have a typical time series because we're not measuring something that's on a continuous scale. We took the data from the respiratory irritation and turned it into just 2 categories, low risk and high risk, so binary, zeros and ones. And from this data, you could see that it's very patchy. You can have many days of high risk in a row, and then it's low risk, and then it's high risk. So this Hawkes process model, it's like a Poisson model where there's an arrival rate or a rate of becoming high, and it's inhomogeneous. So it's not constant. It actually changes as a function of the past several days of high risk. So if there's just one isolated day of high risk, the probability that the next day will be high risk goes up. If you have multiple days of high risk, the probability goes up even higher. And once it goes beyond a threshold, that's where we consider that that's a forecast for the next day being high risk. And that model seemed to do a little bit better than the wind-based model, even though it doesn't use wind at all.
Can we compare them on the basis of accuracy, or are there other metrics we should look at?
We just compared them based on accuracy, and the Hawkes model on average was able to forecast 86% correct, with the highest being 91% at one particular beach and the lowest being 82%. So overall, it seems to do 3 to 4% better, and it in some sense uses less information. It's not using the weather at all. It's just using the past history of presence of red tide.
That's fascinating that, you would have same data set, maybe a reduced look at it, but achieve something a little more accurate. Do you have any intuition behind what could be a root explanation for that?
Well, the Hawkes process model, it's been used to model a variety of different phenomena that are very different categories, from earthquakes to econometrics to gang-related violence. It's a model that works well in situations where there's evidence of clustering of events in time. So what seems to be revealed by the accuracy of this model is that the presence of red tide is a self-exciting process, which we think it's an interesting outcome of this research.
Tell me more about that. Self-exciting is a term I don't know if all listeners will know.
The typical Poisson process, an example that's commonly given is if you're on a country road and you're at one location and you just count the number of cars passing by. There'll be some typical time between cars passing by. Maybe it's 15 minutes. So a Poisson process would say, okay, that is the arrival rate, once per 15 minutes. And there's no reason to expect it's going to change. So that would be a memoryless process. A process that has memory would be an inhomogeneous Poisson process. So it has an arrival rate that can change as a function of previous arrivals, meaning it gets self-excited. So any new event tends to lead to more events or a higher risk day in our context.
Gotcha. Yeah, that makes sense. That the dynamics would be such that, when a bloom kind of gets going, it goes on has a bit of momentum to it. And it seems like the model captures that pretty well. My understanding is correct.
Yeah, you could think of it as when there's a high risk day, this increases the rate, which then will kind of naturally decay back to the unexcited state if there aren't any more high-risk days. But if you have a whole cluster of high-risk days, it can saturate at a very high probability that tomorrow will be a high-risk day.
And do you have any thoughts on further modeling steps? Would it be worthwhile to try some ensembling approach or something like that?
We have a very large data set, and we're only using a little bit of it. Fortunately or unfortunately, as you might want to see it, we have 8 beaches that were affected quite a bit over the past 10 years. So that was enough to train our model pretty well. So we were able to converge to some steady estimates using our maximum likelihood estimation. In the future, we would want to couple the different beaches. Right now, we have a different model for each beach. They seem to be about the same, but we're not using information about the high risk at, let's say, adjacent beaches. It's known that they're correlated. So if you look at a spatial correlation, nearby beaches will tend to have a correlated respiratory irritation risk. But we didn't incorporate that into the model. We just wanted to try the simplest one and see how it did. And of course, there's a lot more that we could use. We could look at ocean currents, satellite data that estimates where this red tide is off the coast. Also use those water samples that are collected on a regular basis, even though the data is often 1 to 2 days old when it's available.
Yeah, that's interesting. Is that the nature of some, bench science process that just takes that long to figure it out? Or that someone's got to go get it, come back, and there's just a delay and a latency, I guess, in the collection?
It's that, they have to collect it by boat and then take it back to the lab. And that's just the limits of the lab work. There's actually some new...
Unless we move the lab to the ocean.
Unless we move to the lab to the ocean, or there's a new idea that's been tried, which is using, they call it HAB-scope. HAB for harmful algal bloom. And you could collect water from the shore and just look at it under a microscope with your cell phone, send it to the cloud, and the microscopic slides will be able to say what the concentration of this bacteria is in the water, Karenia brevis. So, and that could be almost instant. So if that process could be more widely used, then we could get data in real time or close to real time, which would be a big improvement over the current way it's done.
Is there anything about your work that would make it special to the Florida Gulf Coast, or do you think this could generalize to other areas of the world that face similar challenges?
When we look at the parameters from our Hawkes self-exciting process model, we get similar numbers for each of the beaches, and it could be because they're experiencing the same ocean conditions, but we won't really know the answer to that question until we look at another beach that has a problem that is going to require an infrastructure to collect the data. So we're seeing that places along the rest of the Gulf Coast, like in Louisiana, the panhandle of Florida, there's even been reports in California that red tide is showing up there and could become a problem to the point that they need to start their own beach reporting system and report on respiratory irritation.
Yeah, maybe we need to get started immediately so we catch up on the 10-year backlog that's there in Florida.
Yeah, or what we would like to do is we haven't tested it in real time yet, but we think we have this system that we've developed that could provide forecasts. It hasn't been made available to the public yet. So we want to do a test first on the Gulf Coast, see if this model can predict in real time to the point that it would be useful to the public, and then release it to the public. And if these parameters carry over to a place like California, then we'd be ready to go. We just need a reporting system in California.
Could we explore a little bit more about what that deliverable would look like? Does that involve people maybe having an app and that measuring technique you described about, and that goes to the cloud? And I guess what's the broad vision for how these things get taken up in real time and disseminated?
An app, a website, there's already coordinated by our collaborators in Florida at the Marine Lab. They have an app that people are using to report through this HabScope project. It's also provided to the Florida Fish and Wildlife Conservation Commission and also NOAA. It's the National Ocean and Atmospheric Administration. There is a way that this is already being collected. So the system, I think, is in place and could be transferable to other locations.
Well, I'm curious, what's next for you then? We talked a little bit about broad scope things at the beginning. What are you most excited about currently?
Well, with the collaborator at Virginia Tech and also at some other schools, we're actually launching a data science core. This is a new NSF program that's aimed at getting undergraduates interested in data science and its applications. So the way that we intend to implement this is we want to engage undergrads in data and decisions research at the engineering biology interface. And we'll be doing that through a class we call Solving Big Problems with Big Data. It's not just a semester-long class, but students will get excited by hearing problems from stakeholders in agriculture, conservation, water quality, global health, and emergency relief. And then they'll start to think of, what are the problems? And then at the same time, hear about data science ways to attack these problems, analyzing data. And then they'll actually work on the problem the following summer on student teams. So we hope that in summer 2022, we'll be able to have up to 5 student teams looking at and addressing interesting problems, learning about data science as they go, but applying it to things like this Florida red tide problem, but also many other problems that might come up.
Well, it sounds like a fabulous program that's coming together. Where can people follow you online?
They can follow me at Ross Dynamics Lab on Twitter.
Cool. We'll have a link in the show notes. Well, Shane, thank you so much again for taking the time to come on the show and share your work.
Yeah, thank you for having me.
Thanks for listening to another installment of Data Skeptic Time Series. Our guest today was Shane Ross, myself, Claudia Armbruster, as associate producer, Vanessa Bly does guest coordination, and our host, Kyle Polich.